Jean-Marie, thank you very much for your kind invitation to speak. I'm really delighted to be for the first time here at the Collège de France and have a great opportunity to speak. Well, I can speak French, so I'll have to speak English. And because students and postdocs and researchers from Jean-Marie's group today explained me pretty much everything what was in Jean-Marie's lecture, so I was able to understand it in advance in English. Prior to going over this stuff in even more detail, it was really tour de force in French. So I'm coming from Drexel University from Philadelphia. And I'm going to talk to you today about these materials which we called MXenes, where M stands for a transition metal, titanium, vanadium, niobium, X stands for carbon, nitrogen, and they come in a variety of different structures here. And I will not tell you about every single application today, but I will try to give you an idea of what these materials are, what properties they have, how you can tune those properties, and try to give you some ideas of application, particularly talking about intercalation, but in this case of protons, lithium, into these materials to provide understanding of possible applications here. So I'm coming from Philadelphia, from Drexel University. This is our first building from 1892. We have also something which gives connection to Paris. This building was designed by IMP, the same architecture group that designed pyramids of Louvre. And my lab is on this floor, actually occupying this entire floor in that building. It goes far beyond what the picture shows here. And actually, I'm going to start with acknowledgements, because everything I'm going to show you today was not done by myself, spending days and nights in the lab. This was produced by an outstanding group of students, postdocs, senior researchers. Here is much of the group, not everyone, but a large part of the group at our outing in summer retreat in Pocono Mountains here. And also, we work with many people. This is a very short list. In fact, we work with about 20 at least different groups around the world, because we reach out into many fields where there are experts much better than myself, and into some fields where I have very little expertise. In particular, in the field of electrochemical energy storage, we have been collaborating for more than 15 years with Professor Patrice Simon from Paul Sabatier University, from Toulouse, and I actually spent my second sabbatical last year with Patrice. Much of the work I will show you today on the electrochemical properties and application of MXenes was produced in close collaboration with Patrice and other colleagues here. But let me first explain you this family of materials, what we deal with. Those are nanomaterials. Again, golden circles here are transition metals. So if you're looking at the surface of titanium oxide, hydroxide, the surface will look exactly like that here. But what is important here? They also have typically a layer of transition metal atoms in a carbide nitride structure, which can provide a conductive core. So you look at this as a two-dimensional metal with oxide-like surface, or basically hybrid of oxide and metal within a nanometer thin structure. And it gives many unusual properties to these materials, which actually cannot be found in any other material known to date here. But this combination really makes this soluble, water-soluble metals considered to be here, or materials where you can do reversible redox on the surface without killing conductivity, actually leaving metallic conductivity or even increasing it under circumstances here. Moreover, they come in a variety of different structures. We can have, for example, 2, 3, 4, or 5 even layers of transition metals here. And we call them 2-1, 3-2, 4-3, 5-4 structure here. You can have a variety of transition metals, but you can also form solid solution on the metal side, M side, and solid solution on X side, carbonitrides here. So basically, we can create a very large number of materials here. The first MXenes was published in 2011. Michael Naguib was a PhD student at Drexel University, working with my colleague, Professor Michel Barzoum, and myself. And this is a cover of this article. And you see this layered structure looking like thermally expanded graphite or vermiculite clay. Those are not single lamellas. Those are stacks of multi-layers of MXenes. What is also important here? If you look at possibilities, transition metals, those are atoms in blue. Actually, pure scandium MXenes has been reported since the time of publication of this paper. Carbon and nitrogen. You end up just like looking at 4 possible type of a structure, about 100 of combinations possible. Add halogens and chalcogens and OH as surface terminations. You end up with almost thousands of possible stoichiometric structures. Take solid solutions on both M and X sides, and you end up with virtually infinite number of compositions that can be created here. But it's also possible to intercalate all these green marked and green elements between the layers, further increasing complexity. So we have an enormous new family of materials, which was not even predicted to exist and not known just about a decade ago. So how do we make those materials? Typically, they are made by taking so-known max phases. Those are layered ceramics like this one, layers of carbides and nitride, separated by monatomic layers of A element, one of elements from this group. Or layered carbides like zirconium aluminum carbide, hafnium aluminum carbide, other materials like moly, gallium 2C, basically layered ceramics. And selectively etching monatomic layers or few atomic layers connecting carbide nitride sheets away here, because now here before there were strong metallic covalent bonds, you cannot break them by simply mechanical delamination, unlike in graphite or moly disulfide. So you need to etch them. But then you end up with this oxygen, OH, fluorine, other terminations on the surface, and there are now weak van der Waals hydrogen bonds between the layers, so you can delaminate the structure, just you would delaminate same exfoliated graphite or moly disulfide things here. So there are different ways to etch it. I'm not going to go into much details. But when we discovered these materials, just shortly after Gaiman and Vasyolov got Nobel Prize for graphene, there was very little interest initially here. There are so many already 2D materials, a lot of interest here. But as you see, in the last couple of years, research started to pick up very quickly. Last year, there were about 2,500 papers published here. Altogether, if you look at all over Time Web of Science, and I checked 2 days ago, there are 2,600 organizations in affiliations published in MXenes. So really, research is going on worldwide now here. So why? Because really, we have a kind of a very different family of materials from other two-dimensional or other materials. Those are true designer materials. You can find in the world of materials something similar in metal organic framework or covalent organic frameworks, when you can basically play with organic groups and elements and create a variety of structures. Similar ways here. So we can make this M2X, M3X2, so on, structures with up to 5 layers of transition metals. We can make atomic sandwiches where one atomic layer is moly is on the surface and another like a titanium, 1 or 2 layers in the middle. We can make in-plane ordered materials with atomic column alternating of different elements, and if you etch one of them like a yttrium scandium away, you can end up with atomically column region, like a double vacancies rows on the layer. So you can imagine, it's certainly just the beginning here. Last year, there are several groups from 3 continents reported on formation of high entropy multi-element MXenes here. So the field is growing enormously. And remember surface termination. These Tx stand for this oxygen, halogen, chalcogens, hydroxyls on the surfacings here. So we have really a family of materials with this type of properties combining the oxide metal or semiconductor. Moreover, some of them are very unusual for 2D world. Those are like a thickest, stiffest 2D materials. And actually it gives interesting properties. Bending modulus is enormously orders of magnitude higher compared to graphene. So you can get straight layers which will not collapse, not flimsy as other thinner materials. But each of them will have this thickness here. So, and of course, I'm trying to connect today our new materials, MXenes, to the topic of the lecture of Professor Tarascon, intercalation. And actually, intercalation starts from the moment we synthesize these materials. Because what we do, we take this max phase layer ceramic, we etch it. In our group, we primarily use aqueous etching, and we'll only talk about it today. Molten salts, other techniques are also used, but let's limit it to something. So what happens? When we dissolve aluminum, forming fluoride salt, we right away get water or other solvent between the layers. We get formation of salts, and we get protons coming from acid in between, and we get a structure which is intercalated by ions when surface, because transition metal will not stay non-terminated in aqueous or other active solution. We always get functional groups on the surface, so we functionalize the surface of titanium. And again, in molten salt, it can be, for example, chloride pure or bromine or chlorine terminations. And in aqueous solution, it will be simple OH, oxygen plus fluorine, maybe if you H in concentrated HF here. And after that, we can do this delamination in water. What is also very important, you have heard by now about more than 200 two-dimensional material reported and produced. Just a handful of those can be made in any significant quantities. Here, boron nitride, moly disulfide, graphene oxide, tungsten disulfide, titanium disulfide, and a few others. From day one, we were able to produce MXenes in quantities. Here we have reactors for half a liter, 1 liter, 2 liter, and we can produce up to 100 grams per batch here. So if you take two-dimensional materials, you can cover a huge area with this. 1 kilogram reactors already in industry here. And what is important, we can process it right away from solution that we dispersed it in water. And this is, you see, like a 1.5 meter long film. Actually, just 1 micron. This one is supported. If you make it 3 micron, it will be self-supported. You can basically handle it, cut, make a paper, MXene paper airplane out of it here. And what is interesting here, just after drying, we can go, if flakes are well aligned, to over 500, sorry, this is typo, it should be MPa strength here. It's actually stronger than aluminum foil. And it has conductivity, in this case was 15,000 Siemens per centimeter. We can go over 20,000 Siemens per centimeter today here. So you basically imagine, just Professor Tarascon was talking about composition of basically contribution of various elements into batteries. Imagine you replace 70% of copper that is in battery, if I recall correctly the number on the pie chart, by a current collector, which is 3 times thinner, 4 times lower density, so basically an order of minute lighter. Instead of 17% weight, you have, say, 2% weight contribution. It's already by itself can actually be attractive for battery applications here. And sorry? What about the volume? Well, volume is small because it will be like a 3 or 5 micron film. And you cannot actually make a copper foil 3 micron freestanding. And we can make it 3 micron and handle. And of course, copper has a higher conductivity. And of course, if it is 12 microns, say, it will be stronger altogether, not because its strength is higher, just because it's a thicker film here. But at least for prismatic cells, for example, it's definitely work, but I'm pretty sure we can also make cylindric cells with those here. Why can we so easily process it after the solution in water? Because this surface negative charge produced by oxygen OH groups give us from minus 30 to minus 80 actually for some MXene zeta potential, so high negative surface charge around neutral pH region here. So basically these flakes form colloidal solution in water, no binder, no surfactant, no nothing needed. When you dry it completely, they basically stick again back to each other. But also one important thing from other 2D materials. When you reassemble, say, graphene, you can make graphite, or at least disordered graphite structure. You cannot make max phase back. There is no bulk material with this composition because we now have this oxygen as a termination on the surface here. So it's a new material. And if you put a droplet of different MXenes solution in water, you can see it start dissolving like a dye. You saw how many different colors I showed in the beginning here. So we take max phase powder, we etch it, get MXene, and we delaminate it, and this is like a bottle with, I don't know, 10 milligram per milliliter, say if it's a kind of a usual stock solution of MXene here. So water processable, and if you have a colloidal solution of flakes in water, you can basically do everything what people have been doing for decades, if not centuries, with colloidal solutions. You can print it by using any known printing technique. You can do spin coating, sprayed coating, doctor blading. If concentration is high, you can get liquid crystalline behavior. It helps to align flakes nicely, and even in a thick film, if you do, for example, doctor blading things here. But you can also assemble monolayer films at the interfaces here. So again, it's nothing new in processing, but again, the advantage is here. You don't need surfactant, unlike for graphene, many other materials, so you can basically assemble it easily. Now, what are typical properties? Majority of MXenes studied today are true metal with a high density of state at the Fermi level with a high concentration of carriers. Remember, even graphene being promoted as a highly conducting material is a zero band gap semiconductor. You need to create defects or dope it, and by doing it, you decrease the conductivity here. But it varies within like a 4 or 5 orders of magnitude. Niobium to C will be much less conducting because in this kind of a thin structure like that, if you put oxygen on the surface, you put basic electron density away, and you can open the band gap, at least as DFT says to us here. But they're also strong and stiff. Those are flakes produced from solutions, about 20 micron in size. I've never seen titanium or moly, for example, S2 flake larger than a micron. This flake will simply break from vibration in solution here. MXene, we can make it here. Otherwise, they look like other 2D materials. They're single crystalline. You can see it from high resolution TM and from selected area diffraction. And you can assemble them in this multi-layer film. So the film I showed you before, like a long stripe, 10 centimeter wide, meter and a half long, would have a structure like that here. So this one will be freestanding. It's probably about like a 6 micron, so you can basically handle it like you handle a thin paper, things here. Again, this dispersibility as water is important. They're also plasmonic materials. And there are a lot of tricks you can do it with those materials things here. And there are many other properties which are useful, which I'm not going to discuss today, like a tunable chemically work function, conductivity here. Key message I would like to leave you with here. We have a material system where you can tune pretty much all properties as you need. From electronic to chemical composition of the surface, imagine you have pretty much a dozen of transition metal oxides on the surface, and can be hydroxide, and can be chlorides, or other things here. There are, by now, probably, I don't know, definitely more than 1,000 of papers on DFT prediction of properties of various MXenes. There are some interesting things not related necessarily to energy storage, but for example, magnetism, ferromagnetic, two-dimensional ferromagnetic, antiferromagnetic materials, topological insulators, semiconductor, and others. Some of these properties have not been even experimentally verified yet. For example, we can get antiferromagnetic materials, magnetic glass, but ferromagnetic 2D have not been demonstrated. Dmitry Talapin from U Chicago showed superconductivity in niobium carbide terminated by sulfur, selenium, tellurium in 2020. A number of other things have been shown here. But what is important? All these things are controlled by synthesis of this material and their composition. So, material scientists usually draw this kind of a triangle synthesis properties application on synthesis structure application. I don't think it's really triangle. In my opinion, it's always like a sequence. You go start from synthesis, actually from precursor. Max phases, stoichiometry, grain size already contribute here. Synthesis, these etching conditions, they lead to controlled morphology, structure, surface chemistry, defects, stacking, and so on here. And those control properties of the materials. But if we know properties, then we can move to application. Based on properties, we can design application. But again, using current computational facilities, you can actually start with application and properties you need and go back to the composition and structure that may provide you these properties here. We're not completely there with the predictive modeling, but it's moving in this direction. And in some cases, we can control that this is happening here. So again, we etch, remove this layer of, say, aluminum, silicon. We get intercalation of ions in solutions are here. And again, we can control the kinetics, for example, by changing temperature. Etching, you increase the temperature, you require shorter and shorter time to etch. But again, if you increase temperature further, you start creating more defects. You can remove transition metal atoms from the surface. You get high oxidation states. So all these things interplay here. And often you can also get a complex surface chemistry. This is a result, for example, of neutron pair distribution function studies on materials produced by using 10% and 50% HF solutions here. And now we go to much lower concentration, usually here. And you will see the amount of fluorine will increase with increasing concentration. And also we have done similar studies, say, on high-resolution STEM, showing that number of vacancies in the surface layer of titanium method will increase with increasing concentration of etchant here. So you can play with this. So bottom line is, we have this family of materials where you can control the properties by controlling M element in the structure, controlling X element. You can mix them and have solid solution when you have different concentration of elements, or you can order them between different layers here. Then you have surface termination. By removing them or by adding different termination, you can again get different properties. And then you can also graft molecules on the surface. And because of majority of MXenes have, well, even the one with 2 layers, you still affect properties much less than graphene. So in graphene, you get oxygen OH on the surface, make it water-soluble, graphene oxide, and you kill the conductivity completely. In this case, you can graft molecules on the surface, and you can keep the conductivity in titanium-32 because this will be the electrons, for example, of titanium that provide conductivity in this layer. And just one example of how properties change. In addition to, you see, like, for example, different colors give you different plasmons. For example, titanium-32, it's maybe difficult to see here. It's actually green in solution in transmission and reddish in reflection. And titanium-2C, one layer of titanium and carbon less, will be actually green in reflection and red in transmission, because transverse surface plasmon for this one is at 780 nanometer roughly, and this one is 50 nanometer. Actually, if you recall Lycurgus cup, classical example people give from nanotechnology from the Roman cup from 4th century, gold and silver there give you exactly this combination of colors. It's a green in reflection and red in transmission. But on other properties beyond plasmonic, for example, work function, which is very important for solar cells, other optoelectronic devices here. OH termination give you 2 electron volt. Anneal your sample, remove hydrogen and get to oxygen, and you go to 6 electron volt. So again, you have tunable work function just by changing surface termination in these materials here. And this is example, I think it's better, you can see colors here, green and red, titanium 2C, titanium 3C2. Even changes in this surface chemistry will also shift, for example, you remember HF and milder etching, more reduced material. And this is a transfer surface plasmon, and I'll talk a little bit about it further when discussing electrochemistry of these materials here. We can shift its position, really determined just by oxidation degree of transition metal on the surface of the material. And as I mentioned also, you can have defects in these materials here. For example, you can see vacancies in the titanium layers, single vacancy, triple vacancy, a cluster of vacancies, these dark dots that you can see in STEM images. Again, harsher are etching conditions, more vacancies you can get. And they're good for some application. Talk about electrocatalysis, they may be useful. We can place single platinum atoms or gold atom in this location, making very stable single atom HER catalyst, for example. But they will decrease stability, both electrochemical and environmental stability of the material. So again, you need to control. Again, nanotechnology, nanoscience, not about making things small. It's about controlling at the nanoscale. Okay, I hope this gives you an idea of what these materials are. Let me talk a little bit about intercalation and electrochemistry here. I trust you have seen probably this Ragone plot too many times. I know Patrice always shows it in his talks here from our papers here. But again, much of the effort is going on to get into this area on Ragone plot when we can have both fast charging, so high power, and high specific energy here. And we had a nice discussion earlier today with several people about the role of conductivity here. But what I believe is really important with all the battery development ongoing here, if you want to get to high power, there is no way you can have a bulk, large pieces of materials where solid state diffusion will occur within minutes. So if you want to come with your car to a charging station and charge it in, say, 5 minutes, what Elon Musk promised, you really need to have materials where solid state diffusion is minimized or eliminated. Also, what does it mean having fast charging? It simply means you run high current through your battery. If you run high current and your material has poor conductivity, it will simply end up with Joule heating, and consequences of this are very well known. So what I believe we really will need to make it there in terms of power, we need materials that have both ionic conductivity, on the surface conductivity, basically nanomaterials to a certain extent, and electronic conductivity, which allows you to deliver electron to the side also through thick electrodes, not only here. And there are, of course, a lot of challenges here, like ACI formation in batteries, high surface area leading to parasitic reactions. But maybe if you have materials which are kind of assembled, liquid, solid, or conducting solid ionic conductor, MXenes type of structures, you can get basically maximum possible conductivity compared to any other redox material. You can have surface redox because, again, unless you have surface redox, you will be in this range of double layer capacitors here. So to move here, you need to have a redox reaction here. And this is a game we are trying to play, using this in MXenes electronic conductivity to provide faster charging, using 2D galleries to provide fast diffusion of ions, using transition metals in various niobium, vanadium, moly, titanium to provide reversible surface redox reaction here. And also, because of this strength, because of these galleries, it's possible to squeeze zinc, magnesium, aluminum, and other multivalent ions here. And again, I'm not going to give you any recipes today or tell you how to build a battery. What I'm also going to do is to show you some examples of ionic transport behavior, challenges we face, differences compared to other materials, and hope you may find some applications in your system for those materials here. So what happens when we take these two-dimensional flakes assembled into a film and start charging here? First, pretty much we always have ions between the layers. Even from the moment of synthesis delamination, when we use lithium or tetrabutyl ammonium, tetramethyl ammonium ions, we get ions and eventually solvent like water in between, unless you heat it up to a couple of 100 degrees C and dry it completely here. And different ions will give you different behaviors, and actually when you start intercalating into this layer more and more ions, what you will see, sometimes you get contraction because you have negatively charged surfaces and positively charged cations going in between, so there is electrostatic contraction of electrodes here. And there can be almost no change, like in case of potassium, for example, from potassium sulfate here. And there can be, depending on potential contraction and then some expansion things here. So again, it depends. Again, you want to have large expansion if you build an electrochemical actuator. You want to have minimal expansion if you, say, build a battery. Moreover, different ions will bring different number of solvent molecules. This is an example for cosmotropic, cheotropic ions work for Nathaniel Spiegel from Bar-Ilan University. It's XCM work done here. And you will see, for example, some ions will bring water, some ions like tetraethylammonium will push water out, and some will actually little change the volume of water. So you need to account for those things here. But what is important, again, you can work with this example of filtered freestanding film, and this probably like a 3-micron film, and you can see you can handle it, you can bend it, you can fold it. Actually, my students test the quality of film usually. If they can fold it nicely, completely, it means that this is basically mechanically good film here. Now, even if you intercalate different ions and you know whether they bring or remove electrolyte, they also behave differently. Similarly, we can take several single-valent ions, from cesium to lithium. But you see capacitance charge store will be very different. Lithium, sodium will give you much more than cesium, but they all have actually single charge. And the reason is that those are MD simulation done by our Oak Ridge colleagues, Paul Kent and Dean John. Here, you see lithium and sodium will actually come to the surface of MXene, and there will be polarization, and there will be more charge transfer compared to, say, potassium or cesium, which will stay far away. So what they actually showed here is that taking a distance between the oxygen on the surface and the cation, you can actually predict there is a kind of almost linear dependence how much capacitance you have, because this is really like polarization. It's double layer capacitance, but there is partial like a charge transfer. You pull some of the electron density towards these ions. The closer the ion in, even at the same single charge, you basically have stronger polarization of the titanium atoms here. So this is kind of a schematic from simulation showing what happened. This ion, say, sitting in the middle, far away, and there is little effect here, and the closely coming lithium and sodium interact much stronger, and there is stronger polarization here. Now, what is also interesting, it's not like you can continuously add solvents, say water molecules, if you talk about aqueous system, and ions. If you have in this system ions and solvent molecules, water actually will go monolayer by monolayer in stepwise function. If you look at changes in position of X-ray diffraction peak, when you change the humidity from 0 to 95% here, you will see there is no like a continuous change. There is peak here corresponding to monolayer of water molecule, and then it jumps to 2 layers of water molecules. And it will be the same here. And you remember, in case of potassium, there was almost no change in the lattice parameters. And also, when it goes in, it doesn't bring extra water. So it means that you primarily have potassium with equilibrium number of thermodynamically preferred water molecules sitting there here. But again, you have to deal, it means, with different number of molecules as you go basically and charge it here. And in situ X-ray diffraction done here shows very nicely how this basically change happen if you change humidity, and an ion can get more molecules salvating it in confinement. So we get a kind of a special case, salvation by salvation, not in a bulk, salvation in confinement. We have a different number of molecules salvating ions here. And we get this type of, if you look at lattice parameter, jump-wise changes in these things here. And I'm going to skip it further here, but again, it's a kind of we showed it on many different ions here, this discontinuous change, even if you have continuous mass change. You get ions, but at a certain point you make a jump in the behavior, and I will show you how important it is a little bit later here. Now, we get ions, we get water. And conventionally, people predict properties of solutions, and it's all very well known, conductivity and everything else. But what is interesting here? If you look at water, which is confined between these layers of MXene with strong interaction of oxygen OH on the surface things here. What you can find that you actually have lower diffusion coefficient of water compared to bulk. But if you get ions intercalated, there is further increase by, say, roughly 2 orders of magnitude in diffusion coefficient of water. And we did it by 3 independent techniques, actually. We did it by Quent's neutron scattering technique, by prediction, by React-FF simulation, but also we measured very similar behavior by using simple electrochemical impedance behavior here. So we actually greatly slow down this water between MXene layers, so it behaves differently here. Now, we start slowly understanding how the system behaves here. Then the question arises here. Can we really have fast redox at very high rate and still keep a redox reaction when we have high conductivity of MXene and we have ions delivered here? And the answer is yes. What you see here are typical cyclic voltammograms for titanium 3C2, MXene amid TH, it's actually oxygen OH is usually on the surface primarily here, in sulfuric acid electrolyte. What is interesting? If you are at relatively slow rate, scan rate, millivolts per second, 200 millivolts per second. For batteries, most of what you do is a very high rate already. But this is typical supercapacitor operation rate. You see, there is capacitive envelope. Here it almost doesn't change up to 100 volts per second. And there is this peak. And this peak is completely electrochemically reversible. The separation is 20 millivolt between redox peaks here, between the couple of the peaks. But what is interesting, you go to 100 volts per second, enormous rate, 10 millisecond, 1 volt charge discharge, and you still have this peak. So you still have a redox storage at these rates here. So what does it mean? If you have high electronic conductivity and ability to deliver fast diffusing ions, protons, you can get redox storage at virtually any rate. The question is to be able to overcome this limitation. And not electronic in this case. You see, you make electron. This was for 90 nanometer thin electrode. But you go to 3 micron, 5 micron, and they're all aligned this way in this case, specifically so the diffusion path increases much longer, and you see we start losing capacitance. We still can get extremely high rate for even few micron gel electrodes, like a 1500 farad per cubic centimeter, which is several times more than one would get on carbon here. But there is this limit. And we also know from in situ X-ray absorption spectroscopy that this process is a reversible redox in titanium. So X-ray absorption spectrum of titanium shifts up and down. So we go from oxygen to OH, basically, on the surface of these materials. And we also can monitor. You remember initial part of the spectrum, let me just go back for a second, when there is like this really rectangular behavior, XRD shows no changes. There is some electrostatic contraction when more protons intercalate. And then there is this increase. And it seems to be very large here, but in fact it's a half an angstrom. And this is exactly the length of OH-oxygen bond. So you basically switch between oxygen to OH termination, increasing the bond length, increasing spacing somewhat between the layers. Think here. So we try to understand this behavior. And everything what I showed to you was for a single MXene, titanium 3C2, the first discovered and simply most studied. Is it the best material for all application? Of course not. It's a very good material. It has titanium and carbon, which are common elements, abundant, can be produced large quantities. But again, DFT calculation done by Dean Jahn group and Paul Kent group shows that there are many other materials which actually should have a much higher storage compared to titanium 3C2. It's not even close to the best group of materials things here. So again, what we need to do is to look at materials available, predicted properties, and test, synthesize, test those compositions to find better behavior. Now, recall I mentioned this type of a stepwise change in interlayer spacing in MXenes here. So we looked at dilute solution of ions and aqueous electrolyte and protons here. But of course, just like many of you work in water and salt electrolyte, trying to expand the voltage window and increase energy density, we followed activities in that field and tried to see what happens when we put MXene in halides electrolytes. Chloride, bromide, iodide, then we can get lithium TFSI as well, high concentration here. And we found very unusual behavior. This is a curve I showed to you CV with protons, with double layer and this redox peak, oxygen OH. If you have, this is sulfuric acid I showed to you just before. If you have low concentration lithium chloride electrolyte, you will get just the double layer behavior. If you try to push towards positive anodic potentials, there is oxidation of MXene by water. But if you take 19.8 molar lithium chloride solution, so this maximum concentration reach water and salt electrolyte, we can push much further. So you see, we're coming close to 0.8 volt, and there is still no basically water splitting. But we have a couple of those peaks. And when I saw this first time, and actually you can get it, you see with 15 mol, even 10 mol concentration, and it's a first cycle, it's a weaker, and after a couple cycles it develops and remains stable. But if you go to lower concentration, 5 mol, it appears and then start disappearing, degrades. So what happens? Initially I thought it must be a redox couple, or it must be intercalation of anion and deintercalation of anion, because we're in a positive range here. And we actually used a bunch of techniques, including QCM and others, to show that the mechanism appear to be very different. In fact, what happens when we see here charge capacitance? We actually completely discharge everything from between the layers. If you look at mechanical changes, you see delta, the electrode simply shrinks to zero, to dry state virtually here. And then at certain positive potential, there is a rush of cations in. So what happened? Anions don't intercalate at all within this range of potentials. But since we apply sufficiently high positive potential, all lithium ions solvated with 2.5 in average water molecules there per lithium rush out. And electrode simply like closes, collapses. And then when potential decreases to roughly like a 0.4 volt starting here, they go again opening the structure in a step, forming a monolayer of lithium with solvated water molecules here. And then you have a conventional double layer. So if you, for example, stop at this point, you will get just a double layer envelope in this situation here. So again, we have some kind of different behaviors. And you may remember I showed in the very first slide this type of pictures with various colors of MXenes. So, and I mentioned to you that we can, by changing oxidation state of MXene, monitor whether, basically monitor the oxidation state of transition metal, because this is a surface, transverse surface plasmon, only depends on oxidation state. So flake size, lateral flake size doesn't matter, spacing between flakes doesn't matter here. It's a primarily here. So what happens? When we apply potential -1 volt in sulfuric acid electrolyte, from OCV we go from about 800 nanometers to 630 nanometers. So we have 130 nanometer change in the peak position. It's a very visible actually. The film will visibly change between green and blue, and somehow it doesn't really reproduce extremely well colors that's brighter on my screen, but you can basically see it here in green at OCV, it becomes actually blue -1 volt. And you can record it, and you can basically calibrate the shift again, data I showed you from X-ray absorption spectroscopy, and you can know, for example, how much oxidation changes here. And we developed actually a technique which we apply to by now to at least 6-7 different MXene to several oxide and conducting polymer, that allows actually to distinguish between double layer behavior. You have polarization and small shift, and if you plot it as a function of potential, you basically get straight line with a certain small slope. And redox, when you have this major shift, and again, in the range, if you have combination of double layer and redox, you will have a change in the slope of peak position as a function of potential here. And in this case, for example, electrolyte, you will get fast change simply when you get ions in, but total change in the peak position will be much smaller, much closer to double layer compared to redox here. So we know that in this case, this was not redox again. So we basically have a technique that allows us to distinguish between double layer capacitance and redox processes in materials by simply using transparent thin electrodes here. And we can play, of course, similar games with many other MXenes, not just titanium 332. This example, for example, V2C MXene here. This MXene was little used before just because it's considered to be not very stable. So in solution, it would degrade within a day, film would degrade within a couple of months here. But by decreasing number of defects and changing surface termination, we were able to make it very stable here. So what we do again, we delaminate it initially with tertiary amines, but then we replace TMA and TBA with lithium. And what just happened in this case here, when you go from, say, TBA delaminated V2C, and TBA, TMA are very common delaminating agents also for oxides, clays, and dichalcogenides here, to lithium, we basically decrease the spacing significantly here because we get smaller ions here. But moreover, lithium coming closer to the surface, not allowing more water to come in, makes materials much more stable and increases its conductivity. So we go, say, from about 250, 70 to over 1,000 Siemens per centimeter. So again, we can play these games. And let me give you the very last example when we move to organic ultralight. When we look at the same titanium 332 MXene now, not in dilute neutral electrolyte or protic electrolyte or water and salt electrolyte, but further increasing the voltage window, further increasing potential energy density, looking at organic electrolytes. And again, you cannot just simply plug it in somewhere and use here. You need to understand what is happening, how, in this case of confined systems, this electrolyte behave. And we looked at capacitive energy storage with titanium 332 MXene. In lithium TFSI with resolvent, DMSO, acid-nitrile PC. And actually, a precursor to this was kind of a electrolyte genome work done by many in the US, predicting, for example, that, of course, mobility of lithium in acetylnitrile in this salt solution will be like order of magnitude higher compared to PCA, DMSO, and we wanted to look whether it will help us to get good results. But what we found actually, in the case of acetylnitrile, the best electrolyte, we got actually the worst performance. And PC with an order of magnitude lower bulk mobility and ionic conductivity gave us a much larger area under the curve here, much larger capacitance here. So why does it happen? We looked at intercalation process, and actually this was work done at Toulouse on in situ XRD here. And what you find, in case of DMSO, there is large latent spacing between, about 19 actually angstrom going latent spacing here. And in case of acetylnitrile, it goes down to 13, and in case of PC, it goes actually down to 11 angstrom, so with 9.5 angstrom thickness of titanium 332 layer, we get basically like about angstrom in between only here. Moreover, there are relatively large fluctuation of spacings with charge in DMSO. There are some fluctuations at nitrile, and it's very stable in the case of PC. So what just happened here? You cannot predict behavior based on behavior of bulk electrolyte here, on behavior of what we know, for example, for porous carbon materials, for example, capacity. The reason is very simple. In case of DMSO, we get lithium, as modeling showed, we get lithium and we get DMSO. Moreover, lithium stays somewhat salvated. Some lithium ions go to the surface here. In case of acetonitrile, which shows the worst behavior, lithium and acetonitrile go in. But actually, acetonitrile separates, it's pushed out in the layer between the sheet. So basically, we get like a poorly electronically conducting layer of solvent molecules separating layers of MXene here. And in case of PC, we only get within this space lithium. So we get basically like a fast intercalation of lithium between the layers with complete desalvation without PC here. So it just shows how different the behavior can be from what you may intuitively expect based on previous experiences or bulk predictions. So what we are trying to do in our group is really to understand how by confining electrolyte between layers of MXenes and other 2D materials in collaborations here, we can basically control behavior, moving from double layer to this type of a pseudo-capacitant combination of double layer behavior, redox behaviors here, and eventually to purely like a battery-like redox behavior where there is much larger charge transfer from ion things here. Just you can express it like a degree of confinement. And actually there is this paper coming out in Nature Energy in the next couple of weeks with Veronica Augustin, Volker Press, and Patrice Simon, myself, and several other collaborators from our Energy Frontier Research Center, when we try to bring it all under one umbrella and showed for this materials confinement, you don't have like a separate cases of like a double layer capacitance or redox or pseudo-capacitance. You can basically, simply depending on degree of desalvation and confinement, you can basically have a continuous transition between all these charge storage mechanisms here. So it's a fun. Now, let's move from science to just a couple of single applications. What is important now? We know we have this very large family of materials with tunable structure, tunable properties, conductivity, redoxability, transition metal, number of layers, ability to confine and intercalate ions here. What is important? We need to find where they can really do work and where they can be useful here. And one straightforward approach is, okay, let's take these materials and intercalate lithium and get the best lithium ion battery ever. But DFT calculations predict that on the best day, in the best of MXene, like titanium 2 CO2, you can get something like a 400 or 500 milliamp hour per gram, theoretically. Well, you cannot compete with silicon in this case here, less with metal anodes. So again, you can do it, but you're not going to get anything extraordinary. So what we need to look for? We need to look for application first where conventional materials cannot work. Very thin, printable, flexible devices. Wearable electronics, including electronic textile knittable energy storage in textiles that what several students in my group are working on. You can look at not only like printable, actually it's impossible to see here, but there is this basically set of 100 of interdigitated capacitors here. They can basically do AC-DC conversion because of this extremely high storage. So basically, based on properties of low-dimensional, two-dimensional materials, we can do things that they can do. Now, going back to what I mentioned at the beginning here, we have materials with high conductivity, high mechanical properties. Hydrophilic oxygen-terminated surfaces which are oxide-like. And actually, they can act as, say, binders for silicon, for actually even like a porous carbon, because you may think of, say, activated carbon as a highly conducting material. Titanium-32 MXene is 2 to 3 orders of magnitude more conducting than activated carbon. So actually it can make faster electrodes, but also it eliminates polymer binder. So you can make electrode without polymer binders, and currently with NMC we can actually go down to just 3% of MXene and still have nice cohesive electrode when using it as a binder. Struggling a little bit to go over 60 microns of separation from metal here. But again, we can make this 3-5 micron current collectors and build on those, for example, LFP, LTO electrodes, simply making much thinner current collectors, especially for micro batteries, for batteries where you can actually make thinner electrode. Just because now your current collector is thinner, you can pack a larger stack and get faster properties here. So binders, current collectors here. Moreover, there has been a work from probably at least a dozen of different groups around the world showing that MXene layers, unlike copper, suppress growth of dendrites, and particularly working with collaborators at Yury University, we showed that growth happens laterally, totally on the surface here when you grow it, even at pretty high rates propagates here. They have a hypothesis from DFT that hexagonal lithium is formed few atomic layers to accommodate the strain and follow this growth. It's still to be experimentally confirmed. But the fact is the fact, for example, lithium, sodium, potassium have been shown to grow pretty much dendrite-free. At least, again, this is a tricky area for testing, but at least in conditions tested so far. So there is promise definitely for current collectors for metal batteries here. Decreasing the weight, and also MXene, as you have heard, can work safely with chloride electrolytes. So we can reach out into the range of electrolytes, including material where conventional metal current collectors cannot work here. So basically, what I want to leave you with here, that you need to look for applications based on properties and think. So today we were talking about, for example, can MXene wrap up oxide particles, providing an interface which is more conducting than carbon or tunably conducting, just because you can take, say, niobium-2C MXene with 100 millisiemens conductivity. At the same time has oxide-like properties, or stop transport of nickel ions in lithium nickelate, prevented transport to graphite electrodes because again it traps multivalent ion things here. And as you see today, still large part of research is going on the battery. I didn't talk about metal sulfide battery. Linda Nazar was the first to show that MXene again can trap polysulfides, absorb strongly, and demonstrated very stable performance with several MXene in lithium sulfur batteries here. But there are many other applications where again conductivity is used in electronic application, printable electronics here. We can talk about HER, for example, where several MXene were predicted actually to be very close to platinum, and definitely moly-2C MXene outperforms significantly moly disulfide, and applications are possible here. Electrodes are used everywhere. For example, amazingly in electromagnetic interference shielding, within 5 years, MXene became the best ever materials used. Technology has already been licensed to industry. Similar to antennas, you can print 10 times thinner antennas than copper, 10 times lighter, and get very similar attenuation. So again, we looked at this synthesis, how to control the properties, and then to application. What is important because of scalability of the process, we can tackle not only application sensors, optics, electronic with a small amount of materials, but hopefully go into energy storage application and eventually one day beyond here. And the same thing can be done with even biomedical applications, where again, similar way, biocompatibility, plasmon resonances, chemically active surfaces, intercalation ability, electrochemical activity, absorption of urea, and others can actually guide development. So again, we start with properties, we move to applications here. And these applications emerge. It's still a long way to go. If you want to learn more, this recent review article we published last year is a good starting point to learn about MXenes here. There is already an industry association, MXene Association, following Graphene Association started here. So the field is emerging. And again, I hope this talk will inspire some of you to look into family of MXenes as a potential material that can help you to solve problems you are facing in your research. And I will be always glad to help answer questions, guide you through the field of MXenes. And well, this is my very last slide. Thank you very much for information. You want to find more and download this calendar, go to our website and look at what MXenes can do. Thank you.